Hello, everyone, and welcome to our educational session. My name is Paul Arsov, and I'm the founder of the Decentralized Web Project. Currently, we're working on three different projects, but I'm going to mention this in the end of this presentation. So let's come back right to the beginning, where I'm telling you the title of this presentation. It is the current failures of AI and the way to solve them. This is part one of this presentation, and it touches on technology, on artificial intelligence, and the current ways we're driving towards achieving intelligence in devices and achieving this in a computational or artificial intelligence way. It is well known among machine learning developers that many apparently cutting-edge demos are only staged to look impressive by training a model to perform well on a controlled task. If anything unexpected happens during the demonstration, the agent reveals its underlying brittleness. This brittleness is the primary obstacle to wider artificial intelligence adoption in industry. The technology's pervasive ability to address the so-called long tail of um, um, exceptional scenarios. The long tail is the undefinable open-ended space of unexpected situations that arise in real life, to which agents are unable to adapt on the fly. Many such scenarios are unforeseen even by the developers themselves, who are then forced to write ad hoc special case code to account for the growing number of failures they observe. Consider a commonplace task regularly performed in warehouses. Picking, scanning, placing goods. The core floor is relatively straightforward. Pick an item, scan the barcode, place it in a slot. But a number of things can go wrong along the way. Let's say there's a robot and it has an arm, and the robot's gripper may have covered up the barcode, making it impossible to scan. The gripper may drop the item or part of the item halfway through the movement. The robot also may pick up more than one item. The gripper may damage the item it is holding. The arm may be jostled out of the route by a collision with another object. And the package may be empty due to an error upstream. And finally, the robot arm itself must be or may be misaligned, miscalibrated, or damaged itself. As a developer, we may not always predict that such cases will arise, because the task of picking and placing items, like in pick and place scenario, feels so intuitive and simple to a human, and habitually deal with unexpected scenarios without realizing then that they are exceptional. For example, we may automatically readjust our grip on a box if our fingers are slipping, or unconsciously rotate an item slightly to fit it in a tight shelf space. We could even discover and apply these behaviors in real time. Once we have learned to address a particular challenge, repeating the same sequence becomes thoughtless habit added to our ever-growing repertoire of experience. When we later conceptualize this diverse activity using words, we tend to forget the number and subtlety of skills involved, or how often we make minor adjustments on the fly and on the spot. Rather, we draw them all together under a single concept as of picking and placing. Yet every skill we have a name for. So let's say a business skill, artistic skill, basketball skill is the sum total of dozens of, or perhaps thousands of overlapping pockets of individually learned problem-solving behaviors. In fact, we may overlook when we begin training a model. If we could understand how humans learn these networks of behaviors and how they evolve over time, it will be a huge step in the direction of robust AI, one that can handle the long tail beyond what is currently possible through behavioral cloning or reinforcement learning. It would also move AI towards being a true knowledge worker, the equivalent of its human counterpart in breadth and ability. To claim that the human mind is boundlessly creative and adaptable, of course, would be going too far. We're still driven to meet our underlying needs within the constraints of reality and what we have learned so far. And even the best human or AI cannot solve a problem it is unaware of. Nevertheless, what ultimately differentiates us from a robot is our ability to proactively address a problem by stepping outside of the immediate task domain and bringing in new abilities. As a human picker, if a damaged item arrives in our hands and we don't know what to do, we might signal the floor manager to get their advice, or we would just place it away for a further observation and decision. Or we may study the topic independently if the opportunity is available and ask clarifying questions. Each of these is a separately acquired skill conscripted to our immediate need. The goal of this presentation is to describe how our overall space of skills grows, adapts, and is applied in practice, and how the process may be replicated in a robot. So, how to recognize a problem? Situations in the long tail initially arise out of discrepancy between what human recognize to be a problem and what the AI does. As a developer, it is often disheartening to watch our robot blithely veer off course with no awareness of the chaos it is sowing. The robot is like a child who can't grasp why putting cash in a toilet bowl may be fiscally problematic. When you subsequently tell the child, don't put money in the toilet, we are hard coding rules, so to speak. We are explicitly enforcing commands without waiting for him or her to first learn the reasoning and justification behind them. How much better would it be if the child were naturally driven to update his behavior by his own recognition of the issue? Every failure of an AI to address some edge case scenario always begins with a failure to recognize certain situations as problems. For example, a simple routine to scan barcodes can be easily learned via behavioral cloning by training an agent to copy a set of expert demonstration. What the model will not be able to react appropriately when something unexpected happens and it is unable to finish the task. To do so, it must first recognize that there was a failure and somehow relate it to the need to scan. Otherwise, it will continue to replicate what it has been taught to the best of its ability with no awareness that something has gone wrong. When that happens, our only remaining option is to inject our own broader understanding regarding a problem's detection and resolution into the robot. We may do so as a supporting model, a custom reward structure, or even as a plain old software routine. We may also set up intricate monitoring systems to spot what the AI itself does not see. We would prefer, of course, if our robot just understood, meaning we wish it shares our concerns without us having to explicitly enforce them. What makes us notice and address such problems, whereas the AI itself remains oblivious. That something has gone wrong must ultimately be signaled by some input. As we, the human observer, watch the precipitating events, they seem to trigger attention in our mind, one that the AI is apparently lacking. The input is salient because we know from past experience that it's presage higher level issue if unchecked. For example, covering the barcode with a gripper is a problem because we require that the barcode be scanned. Or to phrase it in another way, it is a problem for us when it isn't scanned, when the item isn't scanned. The fact we recognize situation, like for example a box that wouldn't fit in a slot, is a problem, uh, points to influence of a higher level motivator that is driving that interpretation. It signals in what way the outcome was bad. Even a task as routine as picking and placing serves a higher level purpose from which it gains its direction, corrective force and validity. Only by reference to this base motivator can an agent resolve ambiguities and conflicts that may arise during the task. While picking items, for example, if a package has split into two parts, naive robot trained to pick and place would refer to what its education has imparted. It will try to pick one of the pieces as best as it can. We, on the other hand, move one level and consider more holistically what we are trying to achieve. We are hoping to satisfy a customer and they would want a complete product. So we unite the two parts. Um, all justification for our decision comes from high level motives. This provides the concept and reference to guide us aright. Consider how difficult it would be to explain to a socially unconcerned AI that we are trying to satisfy our customers. How could we describe to an AI what a satisfied customer is, or what the definition of an impact package is, and how this should influence its action? Anywhere an AI fails to spot a problem, it is because it lacks this correct relationship to a higher level motivation. This gap in understanding is the reason the long tail is a problem. This is what it means to recognize something as a problem. By interpreting the sight of covering the barcode as an issue, which brings an immediate attention, our mind has the opportunity to avoid bad situation down the line, the situation from which we may not recover. It is trying to prevent a more serious failure by avoiding its casual precursor. It is being proactive, not just not just responding to circumstances based on what it has learned, but also preempting issues that would arise before they actually do. To preempt a problem always involves creating a new proxy task. In this case, learning to avoid covering barcodes. A new task means that a new skill forms around it. Our goal is now to avoid covering the barcode, and we make efforts to improve on that outcome. We could even preempt this intermediate task with another task. We could learn to avoid grabbing packages where the barcode is facing up, thus reducing the chance of covering a barcode. That would create a third level task to support the second level 1. The chain of preempting tasks can go on indefinitely. We have to take a note how this differs from defining failure as a deviation from historical examples, as being out of distribution or unexpected. Any number of deviations from expectation may occur during the random course of events, like for example lighting changes, wobbling cables on your robot arm, and etc. Most of these are inconsequential to the outcome. In fact, robustness in the face of such immaterial variations is a critical requirement of AI systems. The robot must not panic at every flutter or a bit of noise. The AI must only seek to change its behavior when the variation is significant. This, of course, begs the question of what significant means. We have already given a definition. An event is significant if it anticipates or is a precursor to a problem with respect to its goals. This is true regardless of the degree of the deviation. Even a small flickering light might be sufficient. To see, in the sense of to be aware, is to address something as a problem. What we perceive depends on what we need to find. Each new tension forces us to pay attention and look for its resolution. It is the reason we address the situation as a problem in the first place. For example, the agent will not improve the efficiency of its motion unless it is aware of the timing and cost of its action and considers their reduction a going concern. Safety cannot be improved unless the agent can ally the cases of damages and harm, which means it can first spot damage and harm. As new needs cause us to see new things, we create new concepts like safety and efficiency around this. It is possible for a model to learn to build these conceptual structures on its own. Let's not forget we humans conceived of every concept through which we identify and define the problems and sub-problems of a task. We derived notions like derived damaged item, missing item, loose packaging, and etc. As our experiences of failure forced us to discover or invent new problem domains, our skills grew and became more comprehensive. So in principle, at least, these skills can be acquired, even self-generating by AI. The question is how? We are going to look at concepts as bookends. We hinted that the concept we recognize, like safety or damaged items, arise from a need which changes how we perceive the world. Note that the word concept is used in this presentation as much broader than just those we have in English words language. For example, say we're picking items in a warehouse, and we have learned that we should reach for small packages with two fingers instead of the usual whole hand. This distinction originally entered our mind because of some experience of failure when we couldn't pick small items using our regular approach with the whole hand. The action we learned, nuanced, intricate picking, was the resolution. We may add variations to this behavior as needed, such as particular ways of grabbing variously shaped small objects with just two fingers. This specialized activity may eventually come to constitute its own skill by itself. It may be difficult to think of the example we just gave as constituting a concept. The behaviors we learned blend seamlessly into nearby activities, and any concept inherent in the group is only an implicit one, latent within the action. By latent, we mean that a person can manipulate packages dexterously without coalescing of or defining a concept to describe and categorize these behaviors. To become recognized as a concept, the lazy set of behaviors must first be solidified into identifying symbols or words. Until then, the concept remain latent. The reason we may form explicit concept around these behaviors is to communicate and align our actions with those of other people. If a robotics team worked on the above problem for long enough, they would likely come up with a hyphenated term to designate the task, such as fine pick or nimble pick. The consistency of the term's usage across team members is determined by how much they are willing to align and coordinate their definitions. Given more time and social penetration, the concept could even acquire its own words in the English language. Every new word that has entered the vocabulary has done so based on common need. A word serves as a banner around which to rally communal efforts and intentions. So the linguistic side of the concept is just how we use words rather than other actions to resolve the driving tension. There is no functional difference between an implicit concept and an explicit verbal one. Concepts are ongoing behavior modifiers. Their verbal expression in words is just one of those modifications. Even our introspective self-observation, by which we discover which concepts exist in our mind, is such a modification. Um, Underneath of all, our motives drive out these concepts in a continual activity and practice. It is important to establish this distinction here, because as a written presentation or oral presentation, we can only describe the topic using common words, and these are distinct from actual instances or skills in people's heads. So for the purpose of this presentation, concepts will be defined as patterns of how we deal with sensory inputs on a subjective needs-based level. For example, the concept of efficiency is how we address our dislike of expending energy. Safety arises from a fear of harming others or ourselves. Fragility is rooted in our anxiety about damaging something beyond repair. Any internal utility that a concept displays arises from how effectively our mind transfers responses from one experience to another. For now, all we want to highlight is that concepts, in the sense used here, encapsulate skill because their meaning contains both the nature of a problem, a failure, and also its resolution. Consider the concept denoted by the word empty. It implies that a container exists, and this container would otherwise have something in it. Being filled is part of the concept of a container. So this container can also be filled, which is the resolution. We cannot learn the concept of empty without also learning these implications. As another example, damaged items are not inherently distinct from non-damaged ones. Whether or not an item is damaged is subjective call. Damaged implies a form that we find less valuable, and that there was another version of the item in the past that was preferable and undamaged. Thus, the concept points to an activity that draws the agent from detention to its resolution. Between these two bookends, the tension and the resolution, resides the skill domain of the concept. The initial failure is the reason we pay attention to the reason we made space in our brain for responding to these particular experiences. The resolution is where we bring our involvement with the subject to a close, where it leaves our mind. Everything that enters and exists and exits our mind does so as a consequence of these two events. The meaning of any concept is identical with the motive that drives it, as well as the skilled response we learn to address it. These three, the concept, the motive, and the skill, come into existence at the same time. What must now be explained is how a skill forms within these boundaries. Abstractions lack concrete reality. Some of you listeners may have noticed a possible issue in the theory above. For example, we mentioned that the concept for customers, a concern for customers should be the driving force enabling AI to make decisions about the treatment of goods. However, concepts like customer and concept concern are abstract concepts, as are, for example, damage, item, and move. By abstract, I mean that there is no reliable pattern in sensory stimuli that can tell us what is and what is not a customer, or what is and what is not a damage. Shipping boxes vary widely in appearance. A piece of tape stuck on a box may or may not count as a damage, even though the box looks slightly odd because of this item which was taped. But in some cases it may indeed be damaged. To identify it as damaged is a judgment call, and a case for or against that designation may be argued after the fact. The answer may depend on predicated downstream effects. Will the tape get caught on a machinery later, or cause havoc? So it is impossible to hard-code rule by which an AI can identify damage. Rules that may apply in all cases, now and in the future. This layer of recognition may be continually learned and refined through practice. Assuming we want an AI to do so without human supervision, that in turn requires other layers below it to guide its learning, like, for example, customer satisfaction or machine malfunction. These are also abstract, so they need other layers below them, and so on. No basic atomic concepts exist to serve as a firm foothold in its turtles stacked on top of each other all the way down. The only solid foundation to be discovered anywhere is what we may call the hard-coded biological tensions, like pain, hunger, and etc. Everything built on top of this is mercurial and open to adaptation. Even for the most fundamental cognitive constructs, such as the definition of food or methods to treat pain, have changed vastly over time, as has every other concept built on top of them. This may cause readers some concern. It appears that an artificial agent may never fully be able to deal with a simple situation like shipping a product without being trained from the ground up as a complete human being with social needs and psychological competence. Its ignorance of human relationships may hinder it even in situations as routine as moving packages in a warehouse. And in a sense, this is true, but need not be. Our human perspective is not the only valuable one. A bricklayer doesn't have to care about architecture to provide an useful service. Rather, this presentation will come at the problem from the other side. What breadth of skill can we expect from an agent that defines its own skill domains? This presentation began with the goal of creating adaptive artificial intelligence, an agent that can learn many tasks in various environments and situations, and could handle the long tail of emergent issues. One prerequisite is what we not presume to know the right approach to a given task beforehand, nor inject inductive biases prematurely. Instead, this presentation will try to describe how individual domains of problem solving emerge and evolve to fit the underlying needs. The goal is to allow the agent to discover for itself what the right conceptual approach is and what counts as a problem or a solution. In the process, it may build up the concepts we take for granted, like, for example, smooth motion or efficiency or safety or fragile. It may later choose to align its own interpretations with those of other people around it, perhaps because it is useful to communicate with them, though this is not a necessity. All that is required for us is to give the AI the option to do so, and that requires that we tie skills and concepts to the motives that generate them. We should pause here for a moment. At some point, we have to render the machinery described above and make it explicit. Given what was discussed, one would be forgiven for feeling a little lost as where to go next. This is because the various modes of studying and interpreting skills frequently lead us in contradictory directions. When we first think of skills that people or AI can have, we always start by abstracting them as generalities. This is a limitation of language. To schematize things even the subtle idiosyncrasies of an individual mind. The subject matter must be shorn into common words and symbols denoting entities we are all familiar with. So we may say she has strong business skills, just like her father did, as though business skill were single universal psychic entity shared by all who have it. But it is only universal insofar as we all try to converge on our shared use of the term. In practice, reality is specific to two moments, like no two moments are the same. And we must address reality as it confronts us in all its devilish details. As our mind tries to deal with specific situations and problems which arise, it also begins to find unity and commonality between dissimilar moments. That is part of its function. A response we learn for one case can often, though not always, transfer to new circumstances. A particular technique of readjusting our grip on a box, once mastered, will work for boxes of similar size. But if the box is too big or the orientation of our grip is too different, a new routine may have to be learned. Our perception of a skill's universality is our ability to transfer responses from one experience to another. The skill of having a good grip is ultimately the perceived sum total of these small specific abilities, just like business skill or any other skill. This we may readily accept until we start to discuss the details of these individual behaviors with other people. Even if we try to invent brand new words to describe them, we nevertheless must group similar instances under common category labels. Otherwise, how would we describe them? It is useless to invent a word for something that will only be present once. In one person's mind, all definitions require repetitions and correlation across multiple examples. This is what it means to understand, to connect specific moments to general concepts. And so we come full circle to the need to use general terms. To summarize, when analyzing what skills are, there are three-way tug of war between. Like the reality that skills are the aggregate of unique individual behaviors, we must individually learn how to carry boxes of specific shapes and do so in the immediate moment. The second is skills as transferable trends in behavior. Like we can transfer a learned routine for carrying one box to another box if doing so is appropriate or useful. And the third thing is interpreting skills as general concepts. We may discuss how a person is generally good at carrying boxes regardless of their size and shape. And with this said, I'm going to end this presentation. Thank you for coming, thank you for listening, and stay tuned for part 2 of this presentation, where we are finalizing this, and we're going to close and this, like with the current failures of AI and addressing the ways of addressing them. I'm going back to the beginning of this presentation where I told you my name is Paul Arsov. Currently we work on 3 different projects. The first project is about a collection of non-fungible tokens which are based on 3-dimensional objects, and a marketplace for offering these 3-dimensional NFTs. The URL and the name of this project is 3dnft.decentralizedweb.org. 3dnft is written in a way of the number 3 followed by the letter D followed by 3 other letters NFT. Altogether 3dnft. Then there is dot, then there are 2 words, decentralized and web, and they're all together, decentralizedweb.org. Once again, 3dnft.decentralizedweb.org. The second project that I want to mention is a project about building products for charging electric vehicles and switching high power and high currents. This project is based on the assumption that in the future the current way of charging electric vehicles, which resembles the gas station model, is going to become ultimately insufficient, and we have to transition to the parking lot model, where vehicles are parked either at the place of living or the place of work in a high-rise building with a ground floor parking lot or multiple levels ground parking lot. Products which charge electric vehicles are going to be mounted in these parking lot spaces, and we work for building such products. The name and the URL of this project is power.rstack.com. Power is the ordinary word for power, then there is dot, then there is an abbreviation which I can spell word by word. It's Alpha, Romeo, Sam, Tom, Echo, Charlie, Hotel. Altogether it sounds like rstack, then there is dot, and it ends with com. And the third project that we are working on is about intelligent devices, and it's about building software for robotics based devices. And currently we work and we're exploring kinematics of how a body composed with multiple components, it is moving, and it is actually moving based on motors, and we have to control these motors in a specific way for bodies of different purpose and different ways. For example, like a body of a robot with motors which are continuously moving, or like a bipedal robot, or a quadri-legged robot, or an arm which has to move and grip certain things. All these things are based on kinematics and movements and signals which are placed to the individual motors which are driving this robotic arm. And with this said, I will be ending this presentation. Thank you for coming, thank you for listening. Have a nice day, have a nice evening, and goodbye.